torsional buckling. Here you will see that buckling. Here you can see the beam and also the three axes, x-axis, y-axis and z-axis. In x-axis you can see the moment in x-axis, y-axis, the vertical axis, you can see the moment in y-axis, but in the z-axis it's parallel to the beam. Okay. And this, the moment, the z-axis is parallel to the beam, and then the moment is acting perpendicular to that axis, that is called T. Okay. The difference between M and T, all are moment, but there's a difference. In that regular bending moment, you can find that compressive stress and tensile stress. Okay, in torque, it's a beam is subject to torque. You can see the shear stress. Okay, and also the cross section also getting twisted. Okay, that's the difference. And then torsional equation you might study it in your strength of material classes. T by J is equal to G theta by L is equal to tau by R. Okay, here we are, instead of theta in stability structure, we are going to use the term beta. G, you know that modulus of rigidity, theta angle of twist, L length of the bar or member, T torque, J polar pressure, you know that is Ixx plus Iyy. R is equal to the radial distance of point from center of the section. Tau is the shear stress. Torsional load deformation characteristic of structural member. When a torsion is applied to a structural member, the cross section of the member may warp in addition to the twisting. If we are applying a torsion, it is getting warp. If the member is allowed to warp freely, the applied torque is solely restricted by St. Venant's shearing stress. This type of behavior referred to as pure or uniform torsion. In that member, you can find only the shearing stress. On the other hand, if the member is restrained from the warping freely, then there must be some warping torsions. Okay. The applied torque is resisted by combination of St. Venant shearing stress and warping torsion. These two is coming. Okay. This behavior is called a non-uniform torsion. Okay. Then in a uniform torsion, you can find that St. Venant's torsion or shearing stress. In a non-uniform torsion, you can find the combination of St. Venant's shearing stress and warping torsion. This you first you will see that St. Venant's torsion. If a bar of constant circular cross section is twisted by a torsional moment as shown in figure, here you can see the torsion T. The external torque at any section is resisted by circumferential shear stress, whose magnitude varies at a distance from the centroid of the section. These shear stresses are due to the resistance of adjacent cross section to rotate relative to one another. In such member, the angle of twist is B is related to the torque T by the expression T is equal to Gj into d beta by d. D beta, that's a small angle, d is that's a small angle. This way, okay, that shearing stress, I already told you the shearing stress, the extreme end or extreme the perimeter, it's maximum, and that neutral axis it is minimum. Otherwise, the outer surface, the shear stress is more, and the neutral axis it is very less or zero. And a non-uniform torsion. Normally, this non-uniform torsion you can find in that open cross section, I section, or channel section, angle section. If the torsional displacement that produce warping are allowed to take place freely, then the longitudinal fiber do not change length, and no longitudinal stress induced as a result of warping. However, in certain support or loading conditions, in cantilever beam or cantilever fixed support, will prevent the longitudinal displacement from taking place freely. For example, the built end of the cantilever beam, you can see in the figure 3, is completely restrained against warping, while the unsupported end is allowed to warp freely. Okay, that the fixed support is restricting the warping, but it is unsupported in the free end, it's warping freely. As a consequence, longitudinal fiber change in length and axial stresses are induced in that member. The flange bending moment which exists in the cantilever beam in the figure 3 is very zero at the free end of the member to the maximum. That cantilever beam always the fixed support, you can find the maximum one, and then the free end, that moment is equal to 0. Hence, at any intermediate section, there exists a shear force in each flange. Okay, the shear force BF is equal to minus DMF divided by DC. Again, this is from the strength of material. Okay, the slope of a moment curve at any given point is the value of the shear force. Okay, the slope of the moment curve. You have to remember, the slope of the moment curve at any given point is called shear force at the point. Okay, that's called DMF divided by dz. And also one more thing also you remember, the slope of the shear curve at any given point, the value is called load. Okay, load applied to the point. Here MF, in this equation MF is the flange bending moment, and the minus sign indicates that MF increases as Z decreases. Okay, the moment is more, Z is get decreases. For example, at the free end you can see the L. Okay, and then L is getting decreased, that moment is getting more. Since the flange bend in the opposite direction, that shear force in the two flanges are oppositely directed and form a couple. Okay, this couple, which act to resist the applied torque, is called warping torsion. Here you can see that warping torsion in the figure. In the fixed end, that it's still, you can see the I section, and the free end, that's a twisting of non-circular cross section restrained against free wrapping. Now we are going to determine internal resistance of a cantilever beam to an applied torque. Yeah, applied torque, we are going to set T, capital T. Let us take a cantilever beam, one end fixed, another end is free. In the free end, I am applying a torque of intensity T. Okay. Let us assume the cross section of beam is I. A member that is not permitted to rock freely will resist an applied torque by a combination of St. Venom and warping torsion. Warping torsion. Now, uh, torque T is equal to, it's the combination of St. Venant torsion, TSV, and warping torsion. Let us consider TW. TSV is equal to St. Venant torsion and TW warping torsion. Now let us determine St. Venant torsion and warping torsion one by one. Okay, before that, we'll assume the first equation, T is equal to TSV plus TW is equal to 1. TSV, that's very simple, it's the pure torsion. We can determine TSV from the torsional equation, dGj into d beta divided by d, so we consider that is equation 2. This is from the torsional equation. This I'm writing the torsional equation, d by j is equal to g beta. Instead of theta, I'm using the term beta, tau, shear stress, or this is the torsion, this is the polar moment of inertia. You know, polar moment of inertia is equal to ix plus iy. Okay. Based on these two terms, we can determine TSV. Instead of TB, I'm writing TSV. Now we have to determine the TW. This is the warping torsion. Warping torsion we will determine using this relation. VF is the shear force into height. We have I section. Okay. Shear I am applying at the top. We have a perpendicular distance height. Okay, this is like movement. Movement is equal to VF into height. Okay. TW is nothing but a moment. Now we have to determine the VF. VF is equal to minus dMF divided by ds. Okay. MF is nothing but the flange bending moment. Ds that is nothing but the small length. Okay. Ds that's length. Now TW is equal to minus dMF divided by dz into h. Okay. That equation we will call it as 4. We know that moment is equal to EI into d squared x divided by dz square. See, this already we have studied. IF is the moment of inertia. Flange dx squared divided by dz squared. Okay, we know that Young's modulus. I'm calling this equation the fifth equation. Here x is equal to lateral displacement. X is equal to lateral displacement. We have to determine the x. That's very simple. I have already told IF is the moment of inertia of flange. The I beam to flange. The moment of inertia of the flange. We have to determine the x. X is equal to the same. Find the cross section of the I-beam. Here we have a lateral displacement EX. See the angle beta, the CJ from the CJ, and then the height is equal to h by 2. Okay. From the simple mathematical formulation, we know that Ex is equal to beta into h by 2. That equation we will call as equation number 6. Now, we have to substitute value of X in equation number 5. Now equation 5 come. EIF EMF is equal to EIF into h square, EIF into h by 2 into d squared beta divided by dz squared. That equation we will call the 7th equation. Now substitute the value of EMF in the 4th equation. 4th equation, that the warping torsion, the TW of that equation, TW. Fourth is that TW of the warping torsion minus dMF divided by dz into h. I'm substituting the value of EMF. TWS is equal to minus EIF into h squared divided by 2 into dq beta divided by dz cube. We will call this equation the 8th equation. Now, let us consider this time alone. EIF by 2. EIF by 2 is the property, right? I is the property. Property of the cross section. Now we will call this the warping constant. The warping constant we will call this gamma. Now gamma is equal to EIF divided by 2. No, some. This equation is called 9. EIF divided by 2. TW is become I think some mistake is there. E is not the cross-sectional property, right? Is the mechanical property. Right? The property is the IF and I square. That's not correct. IF and I square by 2. E is the mechanical property. Here we have I square. E. That line, IF and I square, that's the cross-sectional properties. E. Here, IF I squared 2. IF I squared I squared. Now, I am rewriting that equation 8. TW is equal to minus gamma E d cube beta divided by dss cube. That equation 9. Now we have already determined that both unknowns TSV and TW. Now the substitute the value of TSV and TW. TSV and TW in equation 1, that's T is equal to TSV plus TW. TSV we have already determined. TSV is equal to Gj into d beta divided by dz minus E gamma into d cube beta divided by dz cube. That equation is called law. It's a very important equation. Now we determine the internal resistance, that's T. It has two parts. One is the twisting part and another one is the warping. Now this equation 11 is called as the internal resistance of a cantilever beam to an upright torque. Now that equation 11 is called as the internal resistance of a member or cantilever beam to an upright torque. These two terms, TW, TSV and